Okay, welcome back everyone to the final talk today and the final talk of the event. So Charles Almeida is going to tell us about splitting of supervector bundles and projective superspaces. So, thanks very much.
Thank you. Thank you, Jetro. First, I'd like to thank the organizers for this wonderful conference and for the opportunity to speak here. I'd like to report on a work I've been doing with Hugo on superalgebraic geometry. And I would like to talk a little bit about the weirdness that appears there today. So, using the opportunity that Hugo spoke yesterday, talked a little bit about physics, I'm going to skip the applications on physics. Would like to say that the idea of studying this weird geometry that we allow anti-commuting variables was born from the necessity of physics. And then, since we like weird stuff, we started seeing what appeared there. And the point is that when we started to study this algebraic geometry allowing these anti-commuting variables, we saw that a lot of weird behavior of algebraic projective varieties appeared, and then we would like to see what we can do to tame them. So this subject is not new. They started around, if I'm not mistaken, from around the 80s. So there was a lot of work done by the Russian school. And, but again, the superalgebraic geometry came in fashion again from the recent years. And in this context, we would like to understand classification problems. We would like trying to classify supervector bundles on superalgebraic varieties. And in order to do that, we need to start studying vector bundles or supervector bundles that has the simplest possible cohomology. And these bundles are these ACM bundles, the arithmetically Macaulay bundle that I will explain a little bit what they are. So the main definitions that I'm going to tell you today come from this paper, from Daniel, Hugo, and Polishuk. And let's start. So if I have a superalgebra A, is a Z2 graded algebra. So that means that I will have elements that have degree 0 and degree 1. And I will multiply the elements of this superalgebra, saying that, correcting the multiplication by a sign. So I will say that I have A times B is equal to minus 1, the degree of A, the gradient of A, the gradient of B, B, A. So if both of them are even variables, or they have degree 0, then they will commute. If one they have degree 0 and the other have degree 1, they also will commute. And if both of them have degree 1, they will anti-commute. So I will call this bracket the Z2 degree of my element. Oh, sorry. I will say that an algebra is a supercommutative ring if, in addition to be Z2 commutative and being associative, I will also ask the ideal generated by all the odd elements, or that is, the elements generated in degree 1, is finitely generated. So this is sort of to say that I have, by the end, asking this, I'm asking to have a finite number of variables, of odd variables. I will call the ring, when I quotient my superring by the ideal generated by the odd elements, the bosonic reduction of B, borrowing this definition from the physicist. That means that I am killing essentially all the odd elements in my superalgebra. I also will say that my superring is split if I can see the ring as the exterior algebra, if there exists a module, and such that I can see my superring as the exterior algebra of this module. This should not be, this isn't a surprise, right? Because the most common example that we know about super stuff is the Grassmann algebra, or the wedge product of vector spaces. So I would like to mark when my superalgebra comes from these simpler guys, and I will call them split, simply like that. Yes, the common example, the guy that we see walking in the street, of example of a superalgebra is the Grassmann algebra. So if we start with a module, or with a vector space, then the exterior algebra of this guy is super, because we know that the edges 2 by 2, they anti-commute. Today, Today here, my main example of superalgebra will be the ring of polynomials, when I consider the letters x, 0 to xn, to be my commuting variables, and y1 until ym to be my anti-commuting variables. So if you want to think in a simpler example of superalgebra, just thinking in forcing these x variables to commute, the y variables to anti-commute, and then you have your first very simple super ring. I will call the dimension of my super ring to be the maximum of such that the power of the ideal generated by the odd elements is not 0. And then, whenever I power this ideal for the next element, for every power bigger than that, it will be 0. It's not hard to see that the odd variables makes this J nilpotent. So you can think about the dimension, the odd dimension, as the order of nilpotency of this ideal. Okay? Not true, but almost true, or true enough for purposes. You can think of the odd dimension of the ideal as the number of variables, of anti-commuting variables that you have in the ideal. Okay?
So n is equal to n.
Sorry?
So n is equal to n.
No. Oh, sorry. Yeah. So yeah, exactly. Yes. It shouldn't be. I should have put m there. It's not n. M. Sorry. Thank you. So now we have super ring. If we have a super ring, we can try to do super geometry, like associating to this ring a scheme in the same sense that we do working, I don't know, with Hartree. So if we start with a super ring, I say that the super spectrum of my ring is the local ring superspace that I'm saying spec A here, which would be a pair, the topological space minus a sheaf of functions, the structure sheaf. When the topological space is just the spectrum of the bosonic part, of the bosonic reduction of my ring, and the sheaf to be the sheaf of Z2 graded commutative superrings on that guy, that I'm just defining in the sheaf in the basic sets, just saying that I'm applying the sheaf in the basic open will be the localization in that element. So it's the same construction that we do for the algebraic geometry. We do this considering now super rings, right? There's no difference there. And now we can pause a little bit to think about it, and then we can see that a super scheme is not than a regular scheme, but now I'm allowing my functions defined on them to be anti-commutative. So as topological space, a super scheme is nothing that just the topological space of my regular scheme. And that's why when they started studying this stuff, they say that this is the body of our scheme, and the sheaf of regular functions defined the soul of super scheme, because actually the real information that lies in the sheaf and not in the topological space. Okay? So the most basic example of super scheme is the affine superspace, which will be denoted here by K and M. And this is just the pair, Kn, the affine n space that we are used to it, but the sheaf of super functions that we are allowing there is that O, K, and M. So now I'm allowing M odd variables to appear there. This is defining just the spectrum of the bosonic reduction plus the spectrum of the structure sheaf that I just defined for you. And this also can be seen as take the topological space, take the regular sheaf that we know there, and just twist it by the exterior algebra of the even variables. So this is the same. You can think this stuff in the two possible ways. It will be the same.
So in your definition of opens, you allow to invert odd variables.
No, my opens, I'm just allowing to invert even variables.
You took F in A.
No, it should be in the bosonic reduction, sorry. Yeah.
Anything odd is important anyways. It would have been the same as just inverting an important element of the usual.
Exactly, yes. So we also be working in the category of Z2 graded OX modules, but now we are working on the super scheme and our ringed superspace. So there we can define this end of functor that will reverse the parity, and we call this end of functor pi. This end of functor is important because if we start with just a vector space or just a regular sheaf, whenever I put pi in front of it, it will invert the grading. I will say that whenever I had even elements, I will have now odd elements by declaration. And of course, if I apply pi twice, it will give me identity. It will do nothing. This pi is important because it will produce examples, families of examples for us, for the objects that we are used to work. And if we start with a locally ring superspace, we can consider the homogeneous ideal, now the sheafification of the odd elements. And this will give this exact sequence, which I like to call the fundamental exact sequence. Because we have the sheaf, the ideal sheaf of the odd elements lying inside the structure sheaf of our super scheme. And the quotient is just the structural sheaf, this quotient there, is just the structural sheaf of the scheme of the bosonic reduction or the even part. So we sort of can relate the structure sheaf of our super scheme with the structure sheaf of the scheme, or just of the bosonic part, the body of our scheme, right? So this sequence will be important in this sequence, in the following. And if we also would like to control the dimension of a super scheme. So the even dimension is just the regular dimension that we are used to do it in the topological space. And the odd dimension is the supreme of all the odd dimensions of the local rings to every point. So I have defined the dimension for super rings. My stock is a super ring. I can define the dimension of this guy as a supremum of all these possible rings. And then the dimension of a super scheme or for a super ringed space will be just a pair, even dimension, odd dimension. And it is to see that the dimension of the affine superspace is just nm. Our example. Well, if we want to study sheaves, reflexive, torsion-free, locally free, we would like to somehow try to relate super sheaves defined on the super scheme to sheaves defined on the reduction, on the classical scheme that we can relate in my super scheme. In this way, it will be nice to have a way of doing this naturally, given a super sheaf defined or Z2 graded sheaf defined on my super scheme, I would like to relate it with a sheaf in the bosonic reduction. And this is done by degrading. I define the grading of a sheaf to be the sums of all these possible quotients. But since these quotients are annihilated by the J ideal, this defines a sheaf on my bosonic reduction. So there are sheaves of all X modules, OX, the bosonic reduction of my guy. So if I start with a super sheaf on my super scheme, taking the graded the grading of the graded piece of my sheaf will give me a sheaf in the bosonic reduction. And special for me will be the zeroth part of this, which is the quotient of my M by the ideal generated by all the odd elements. And I will call again this guy the reduced sheaf associated to my M. So again, the reduced sheaf is again a sheaf inside my bosonic reduction on a regular scheme. The point is that if I just consider this sheaf, I will lose a lot of information about my sheaf, my original sheaf, and I don't like to lose so much information. Of course, if I reduce the structural sheaf, the super sheaf, I will arrive in the sheaf of my bosonic reduction. And of course, again, we can prove that the reduction is nothing more than taking my sheaf and tensor it with the structure sheaf of the bosonic reduction. This is just a quotient of rings. So we can define quasi-covariant sheaves, covariant sheaves, reflexive, torsion-free, locally free. Define the same setting that we defined the regular ones, the classical ones. We define also the rank, but now we have also an odd rank made by the odd elements in my sheaf, and then I just have a pair for the rank. If I have a rank PQ locally free sheaf on a super scheme, then I can write the reduced locally free sheaf associated to this guy as a sum of two locally free sheaves, where E0, E1 are rank P and rank Q locally free sheaf on my X and on my bosonic reduction. And I'm just using the parity functor here, or pi, to define to declare who is odd and who is even. So that's why it's easier to work on this using this pi, you know. And for a covariant sheaf, we can define also the dual in the same way we do in the classical case. Just consider the home to the super structural sheaf. So, as I say, we have to do this very calmly because there's a lot of stuff that should be true, and but in the same way they should be true, we need to prove because it's a new subject. So if we start with two Z2 graded OX modules, we would like to know that taking the tensor power of the reduced part of these two OX modules will give you just the tensor power of the sheaves, and then reducing. So this is a matter of we can reduce the operation of reducting with the parentheses, and we can. And also, if we have a locally free sheaf E, we would like to interchange the parentheses, the reducedness, the reduction operation with the dualization, and then this works. I should call your attention to the fact that this works for locally free sheaves, but this doesn't work for torsion-free sheaves in general, for sheaves in general, so one must be careful. And just a sketch of the proof. You prove this by, I like to say that you prove this by proving, so you open one side of, you open one side of your equality that you want to prove, so we start with the dual of the reduced. You arrive in this guy, and then you open the other side, you arrive in this guy, and then what you do is to prove that these two guys are isomorphic. But then, since you are working on a local ring space with a locally free sheaf, you can just consider the structural sheaf and prove this for the structural sheaf, and this works, and the proof goes like that. And okay, so the first, yes?
Why do you have a morphism? Is clear that you have a morphism from the...
No. You need to define this morphism, yeah. So it's not clear how to define it unless you have the structure sheaf, E to be the structure sheaf. But since the question is local, you can reduce to this problem. This is what I'm saying. And okay, so we have a little sanity. We can interchange parentheses when is needed. Now we continue with the study. And whenever I have a super scheme, I can have the bosonic reduction, and I also have an inclusion of my traditional scheme, my classical scheme, inside the superscheme, which is denoted by my I here. And this will induce our epimorphism, induced by the epimorphism on the structure Sheaves, right? Because I'm just quotient by the ideal, so I use the dual operation. And we'll say that our superscheme is projected whenever I had a map that reverses this inclusion. That is, I will have a map to from my superscheme to my bosonic reduction, such that the composition to this natural inclusion is the identity. But if I have this map, this will cause my fundamental sequence, if you recall it, to split, right? Because this map will give a section of that sequence. So I can write my structural sheaf as the sum of the bosonic part plus the ideal generated by the odd elements. But topologically, P is the identity. Just the identity. We are not doing anything in the topological space. P is just doing something in the functions that we are considering. So we would like to make this more precise. We would like to say, okay, P is a map from my superscheme to my bosonic reduction, so I can compare a structural sheaf of different stuff. So I'm marking that I'm writing my exact sequence like this. So I'm using my P to remember that the OX, calligraphic X, is a sheaf on the superscheme. And whenever I write the push forward, I'm considering them as a sheaf in my bosonic reduction, just like that. Okay, so then we are more or less in the second part, finished just the second chapter of Hartshorne. We talked a little bit about schemes. We talked a little bit about sheaves of OX modules. Now we'd like to talk a little bit about cohomology. And then to define the cohomology on a superscheme, we remember that when we defined that for regular schemes, classical schemes, we did cohomology of abelian groups. So again, we can just forget the grading that we are considering and just make cohomology of abelian groups for these super sheaves. This will work. And when we have that X is projected, that means when X comes with that P, then just to mark that we are doing the cohomology in the bosonic reduction, we will change the F to the push forward. But since the cohomology is just in the topological part, this changes nothing. It's just a matter of precision for what we are doing. Okay? So we define the cohomology of a supersheaf as forget the grading, do the cohomology for the abelian, as sheaves of abelian groups, and take the result. Okay, so we have projected schemes. But I started this talk, more or less, telling you that the example that you see in nature of super stuff is the exterior algebra of a vector space. So, and we would like to have something similar working for super schemes. When can a super scheme be the simplest possible? And this will be when we can see the structure sheaf of my superscheme as the exterior algebra of some locally free sheaf in the bosonic reduction. Because then the structure sheaf that I'm defining for my scheme is just the exterior algebra of this vector bundle, meaning that locally this will be just the exterior algebra of some vector space. And this motivates the definition that I'm saying that a superscheme is split if the quotient of my ideal by the ideal square is a locally free OX model in the bosonic reduction such that the structure sheaf is just the exterior algebra of this guy. But this means that we can, start with your favorite scheme, classical, take a vector bundle on this scheme, take the exterior algebra of this guy and declare that this is the odd element, generates the odd elements. And in this case, the graded guy of our sheaf, the graded object of our sheaf is just the wedge power of the sheaf that we started. So this is very convenient. And also, it's very easy to show that split superschemes are projected. So we can construct a section to the super fundamental sequence. And we also can, well, I defined the superspectral. Of course, I can define the superproj. So we can also define super projective schemes. And by just mimicking the construction that we have for projective spectrum of a super ring. Again, in this work, we'll be just interested in the case we have the projective superspaces. So I have n+1 commuting variables, which I'm calling x. And I will have m anti-commuting variable that I'm calling y, that I tell you before. Here. So if I want to construct this superprojective scheme, P and M, the superprojective space, I'm just considering the superprojective spectrum of this guy. Again, the topological space will just be Pn, but I am allowing m free odd variables here. Okay?
Does it work to have O1 tensored by the commuting part? So you have some O1?
Yes.
We have a projective space.
Exactly, yes.
There is a notion of
Yeah, we would, yes, but we have, yeah. So, well, we can define the just define the superprojective space like that, but we can prove that the superprojective space is actually a split superscheme when we consider the vector bundle, the initial vector bundle that I told you, just the stereo algebra of O-1, m copies, where m is the odd dimension of our projective scheme. So this creates the odd variables for our superscheme. So since it's split, it's also projected. Now, this you asked, right? Yeah. So if we have a big-graded module, we can denote the Q homogeneous part, the Z degree Q, and we can twist the degree of the module in the same way we do in the classical case, by R, and we just shifted the Z degree by minus R when you do that. And also, we know that the R part in degree S is just the S plus R part. With this, we can define the rank 1,0 sheaf OXR, the super twisting cell sheaf, as the localization of the initial ideal with the initial super ring that we started. So everything that we have in the classical case, we have here for the super, we just have these anti-commuting variables. And we also define the twist of a covariant sheaf by the tensor power of our sheaf with the super twisting set sheaf. Okay? So this is very standard. Anything that you can find in Hartran, we're just allowing super commutative variables. And now we would like to understand what happens. Well, we can do two stuff. We can start with the bosonic reduction, the structural sheaf of the bosonic reduction, twist it in the classical sense, and we would like to see what happens in the super sense. Or we started twisting the super sense, and we would like to understand what happens in the classical case, and this is the content of this lemma. So I'm saying that if I start with a bosonic reduction and then pull it back, and then pull it back, that will be the R twisted of my super sheaf. And I'm saying that if I push forward a twisted super sheaf, this will give the push forward of my guy times in the bosonic reduction, the classical twist, set twist sheaf. Okay? Well, this will give a way of having a very nice way of grading, knowing the grading of the super sheaf. Because if I start with a splitting super scheme, so I know that my superstructure sheaf comes from a vector bundle which is a line bundle. Because I would like to mimic the case of super projective space. Then we can write the grading in the superstructure sheaf just by the grading of these line bundles. So I know precisely the cohomology. I know that I can do the cohomology of this guy, of the abelian part, of the thought as abelian group. Now I can think of it grading with my Z2 grading guy. Okay? This is not too important, but it's just so you can know that we can induce the grading of the sheaf now, of the structure sheaf, using that push forward. Okay. Okay. But I promised to speak a little bit about super ACM bundles, super Horrocks criterion. And then in order to do that, we need to define the raw module, the ith raw module of something. And this is the same that we have in the classical case. So if I have a super scheme, I start with an ample line bundle. If I have a covariant sheaf and define the twisting by this, I define my ith raw module as all the possible twists of the cohomology. Each A will give me Z grading, right? And then with this, I can have a Z grade on my module. And we can prove that each I is also Z2 graded. So this will give me a Z super graded module. Okay? This will be, this is the same definition that we have in the classical sense, but now, yes?
Sorry, I missed the, so what was your definition of line bundle? Was it a 1-0?
1-0, yes.
1-0?
Yes. Yeah, you can think on this. I didn't want to define it on P and M, but we can think just on the projective superspace. And yeah, so the ith super Hall module is just all the possible twists, the cohomology of all possible twists of my sheaf. And okay, so before going further, a very classical result by Horrocks say that if I have a vector bundle on Pn that doesn't have all the Hall modules in the intermediate cohomology from 1 to n-1 being 0, so without intermediate cohomology, then the bundle should be sums of line bundles. And this is what we are trying to tackle here. We would like to have a similar result, and that's why we are doing everything here. So we have the Hall modules. And in order to do this work with the Horrocks result, we will need this, what I call it, the key theorem. That says if I have a projective superscheme, then if I have an element on an isomorphism between two sheaves, it will be an isomorphism. Two locally free sheaves. It will be an isomorphism if and only if the bosonic reduction of my morphism is also an isomorphism.
Sorry, but this is
Yeah.
a definition, no, this is a theorem.
This is a theorem, a key theorem.
So it is automatically full rank also on bosonic part. If you have an isomorphism on the commutative part, it is automatic.
Exactly, yeah. But as the bosonic part, yeah, needs to be the reduced of someone, you know? Yeah, if it's the morphism, the bosonic reduction is isomorphism if and only if the morphism, supermorphism is isomorphism, but needs to be the bosonic reduction, the precise bosonic reduction of the map. So this is what I'm denoting here by phi times the identity on the bosonic part. Okay? This is a matter of supercommutative algebra, more or less. And we proved that the Berensenian of the maps doesn't vanish. So the Horrocks result that I told you says this. If I have a rank R vector bundle on Pn, such that the Hall modules vanish for 1 to n-1, then my vector bundle splits as sums of line bundles. And of course, if my vector bundle splits as sums of line bundles, the Hall modules will vanish. So this is a characterization of bundles without intermediate cohomology. This works very nicely for projective spaces. This doesn't work for other classical algebraic varieties. For instance, we have in the Grassmannians bundles without intermediate cohomology that are not sums of line bundles. But, well, if you are studying superalgebraic geometry, you would like to have similar results from the classical part to the super part. And we would like to have this result for projective superspaces. So what can we do? The proof of this theorem goes in the following line. You do by induction on the dimension of the projective space that you are considering. So you need first to kill the case when n equals 1. So this is Grothendieck splitting. And then you would like to have a Grothendieck splitting for superprojective spaces. So the first thing that we would like to prove is that on P1M, you have that all vector bundles are split as sums of line bundles. And already these results fail. So if you consider the super tangent bundle of P11, this bundle doesn't split as sums of line bundles. You can actually prove it by computing the transitions functions of the tangent bundle, but you also have a simpler proof used by cohomology. Because if since the rank of the tangent bundle is 1, 1, if it splits, it should be written as this. And if you compute the home of this guy from himself, you have these three possibilities. So in the even part of this vector space, we only have 2. And in the odd part, it will depend on how A minus B, it's bigger than 0, smaller than 0, or just A equals B. And then you compute it by hand. And then you have one way of computing this, which is this. And in superprojective spaces, you have something similar to the Euler sequence, which is the Euler supersequence, which is this one. And you prove using this sequence that the home of TP1 to TP1 is 3, 1. And this is not compatible with what we had before, if you recall. You have in the even part 2, and now you got 3. So this means that the tangent bundle cannot split as sums of line bundles. Okay? So already our initial step for the proof of Horrocks doesn't work. So we need to work around and see what we can do. And the main result is with Ugo and Dario, in which we will have a stronger vanishing. And then we will discuss, by the end, we will compare this vanishing with the this vanishing with the Horrocks vanishing to see what goes wrong. And now, if we start with a PQ supervector bundle on P and M, I'm asking n to be bigger than 2. So I'm starting on P2, such that both the Rahl module of my bosonic reduction of my bundle is 0 for 1 to n minus 1, plus this should be a Pn. The AG1, the first Rahl module of the ideal of J, my bosonic part, times E is 0, then my bundle splits as sums of line bundles. So this is slightly different from what we have before from Horrocks. And this implies, this is depending on 2 different vanishings. The vanishing of the reduced part of the bosonic reduction of my bundle, plus the killing of this cohomology. I will just give a quick idea of how we do this. So, fixing the integers, if we had that this guy doesn't have cohomology, if you remember, I said that the bosonic reduction of a bundle will be just the sums of 2 bundles, where I'm correcting the degree of one using my endofunctor. But then I'm saying that the cohomology of this guy vanishes. This will imply the cohomology of these two guys will vanish, right? So I'm saying that by hypothesis, the cohomology of E0 and E1 vanishes. But then I have vector bundles on Pn without intermediate cohomology. This means that I can split them. So the bosonic reduction of my bundle actually splits if I have the hypothesis that it doesn't have intermediate cohomology. Now you can guess that we use the splitting on the bosonic part to define a guess for what should be the splitting of our bundle in the uppercase, in the supercase. So repeat the twisting that appeared. And we have our F. Now we would like to prove that there is an isomorphism between the F that we have just defined and our E. But by construction, we can find a morphism between the reduced guys that is an isomorphism. And we would like to see that there exists a map on these guys that coincides with the bosonic reduction. This is why I stressed that I need this guy to be the bosonic reduction of someone before, you know. Because what could happen is that you have an isomorphism here, but this isomorphism never lifts to the upper part. So first we note that if we start with a map on with a map between the bosonic reductions, this becomes a section in this twist. So what we really would like to see is that, so that guy is just a map on the sections of this bundle, and we would like to see if we have a map on the sections of this bundle, right? So what we have is now is this exact sequence, which I wrote there. I take the long exact sequence in cohomology, and I will have like this. And we know that this guy goes in age 1 of J, E, F dual. And this continues. Now our section lives here. We would like to lift the section here. This will happen if this map is surjective. One way of showing that this map is surjective is showing that this map is, this cohomology is 0. But if you remember, I asked that the cohomology of my guy, age 1, J, A, for every possible twist is 0. And you should recall that F is just a bunch of line bundles. So if this is 0, this kills this cohomology. That means that I can lift this map. Okay? Oh. From the long exact sequence in cohomology, we can see that the double extraction line in the age 1. But then, since by hypothesis we ask that the age 1 group is 0, that means that we can lift our map. So from our key theorem, we know that we have an we know that we have a map such that the bosonic reduction is an isomorphism, This means that our map is also an isomorphism between supervector spaces, supervector bundles. And okay, so you could ask why we didn't prove the super Horrocks theorem. Why we didn't prove that? Why we are asking these both vanishing, instead of asking for this vanishing, right? And what we can prove is that if we have that the age1 of the reduced of the bosonic reduction of our bundle is 0 for the intermediate dimension, plus the age1 of this guy is 0, then we can prove that the Hall module of this guy vanishes. And for some time we tried to prove the converse, right? Because the converse is the true Horrocks theorem. But the problem is that the converse is not true. If we take the cotangent bundle on P2, P2, you do a lot of hardcore computations and show that if it splits, it will have a similar contradiction to the one that we found for TP1. And you also can prove that the cotangent bundle doesn't have intermediate cohomology. So this means that the previous result here is actually what should be the Horrocks result in super projective spaces. You cannot improve it by considering guys with vanishing intermediate cohomology for everyone. You need this stronger vanishing. And yeah, so this is the beginning of the program of trying to classify bundles on PNM. Which I hope I have showed you that it will be a little more hassle than the ones of classifying bundles on PN, because the ACM bundles are just the ACM bundles are just the building blocks for the derived category. If you want to classify them using monads. So already in PNM you have more bundles than just line bundles to think about it if you want to find the generators for the derived category. So if you are really interested in classifying bundles on PNM, you should be aware that you have trouble. And that's it. This is what I wanted to tell you. And I finish with the idea of bento things whenever I'm saying I do super mathematics. And thank you for the attention.